simulations of DC-DC converter by using NI multisim. Okay, I'll discuss about the very simple theory. That theory you know. Okay, so after that the simulation will be shown by Ramaprasad sir. Okay, so some of the simulation will be shown by us. Then rest of the thing you have to complete in your hostel. Okay, basically you know that basic DC-DC converter. Basically you have already completed 6 or 7 experiment. I think so. 6 maybe. I just let me recheck. Okay, so first one was half wave, then full wave, half wave with RL load. That was the first experiment. Second experiment was full control and uncontrolled full bridge rectifier. Okay, with RL and RLE load. I think so. Then asymmetrical and symmetrical bridge. Okay, sorry, asymmetrical and symmetrical semi converter with RL and RLE load. That was experiment number 3. Then experiment number 4 was 3 phase. Okay, 3 phase uncontrolled and full controlled converter with RL and RLE load. Okay, then experiment number 5 was your semi converter, 3 phase semi converter with different load RL, RLE. Okay, then experiment number 6 was ACR triggering circuit and IGBT and MOSFET triggering circuit, means isolated, non-isolated. That was experiment number 6. Right now we are in experiment number 7. Okay, in experiment number 7 today we are going to discuss about the simulations of the basic DC-DC converter by using multisim. Okay, that is your experiment number 7. Okay, all of you just note it down. And here the basic objective of this study to simulate the very common used DC-DC converter. So what are the very common circuits are there? You know that one. First one is your buck converter. Okay, then boost converter. Okay, and buck boost converter also be there. That is your boost converter. Okay, then you can see the NI multisim circuit. Okay, after that you can solve you can simulate the buck boost converter also, but here I am not going to simulate the buck boost converter. Then I will go to the asymmetrical bridge converter. Okay, here you can see the asymmetrical bridge converter. Okay, asymmetrical bridge means it's a DC-DC converter, and every cases we are going to design the duty, calculate the duty. Okay, duty cycle. Okay, in asymmetrical bridge converter it's look like a breeze. Okay, so you know two switch are there, S1 S1 two control switch are there, S1 and S4, and two uncontrolled switch, that is D2 and D4. Okay, the switch are there. So here I am using the pulse wave. Okay, means pulse the signal. Okay, which having 6 volt maximum pulse. You can see that on time and the total time period. Okay, so when it will be on, so you know that load is there, RL load. So here you can use all the converters for R load, RL load and RLE load as per your idea. You can use it. Here the simulation is computed through the RL load. Okay, so RLE load also be possible. And the two mode diodes are there, that is for asymmetrical bridge, and we are also going to calculate the duty. Okay, then the circuit specifications also given here. Okay, so what are the important circuit components we are considering for multisim? Okay, sorry, considering for asymmetrical bridge in the multisim platform. So that I have been considered here, and the values are already given. Okay, so these all are the very brief layout. Okay, very brief layout, but when you are presenting, you can see the gate pulses. Okay, so gate pulses, when you are preparing, so you should prepare the elaborate one. So only some results are given as well as the gate pulse and the circuit. So that I have been simulated. So I am put the all those simulation results here. Okay, and you know the waveform of the current waveform and the voltage waveform. Okay, of your output voltage waveform and inductor current waveform for asymmetrical bridge converter, then we can go for full bridge converter. Here you can see the full bridge converter. How it will be look like that? You can see the circuit diagram of the full bridge converter. Okay, so in previous case asymmetrical bridge we are only using two mode diode. Okay, a muon diode, diagonally they have placed opposite to each other, diagonally opposite each other. In between one loads is there, RL load is there. Okay, and here we are using the mode diodes. Okay, so all four are maybe operable in four quadrant. Okay, so four quadrant operation is possible. Okay, that's why I'm telling you na RL load, RLE load also been possible. Normally four quadrant operation you can observe for your different braking configurations, braking and reverse motoring configurations. Reverse motoring means braking, reverse motoring, reverse braking. Okay, so that means plugging, regenerative braking, dynamic braking, plugging. Okay, all those conditions is possible for this one. Normally we are using this configuration for the DC motor control. Okay, speed control of the DC motor in four quadrant operation. So duty we can also calculate it. How to calculate the duty? So we should get the output voltage here. Okay, so on here you can see the current probe is there. Okay, current probe rating is 1 millivolt per milliampere. Okay, so here you can also find out the output voltage. Okay, so if you have the output voltage, so you can see for the turn on condition what will, how to get that average value, V average. It's a DC converter. You can see that input is your DC, this is your DC input. Okay, and input capacitor is there for sometimes what happen, we are using pulsating DC. Okay, so some capacitor is there, that capacitor is known as DC link capacitor. Okay, sorry. Okay, so it's a DC link capacitor, rating you can see 1000 microfarad and voltage is 100 volt. Okay, so it's a DC capacitor, means electrolytic capacitor. Okay, so it behaves like a DC link capacitor. Okay, so output voltage, how to find out the average output? So average output, V average equals to, so your output voltage V out into T on. Okay, into T on plus V out into T off whole divided by T on plus T off, means whole divided by, you can say like that, only time period. So after getting all those things you will find out the average value. Okay, average value of your output. So that's the concept. It's a simple concept, so nothing big problem is there. If you have all those value, duty means T on T off time you are getting from here. So duty you can calculate from the study. So how to find out the study? So you know the sequence of the gate pulses. Okay, so another conditions may occur, I am coming that point. So you can see that output voltage is like that. Okay, so output voltage is like that. It's a inductor current and inductor output voltage. Okay, both are there. So average value, you can see it's look like a pulsating type value. Okay, that's why that output average voltage is important. So this is your on time value. Okay, so if you have that value, okay, the green signal you have it. Okay, green signal, if you can multiply that V out into T on, so on time, this on time durations. Okay, so V out into T on plus V out, that negative side voltage, that is negative voltage, into T off. Okay, whole divided by T on plus T off. So that will be your average value. Okay, that will be your average DC value. Okay, so it may come positive as well as it may come negative based on your T of duration. If your T of duration is more, so definitely it will come the negative one. If your T on duration is less, okay, sorry, T on duration is more, so it will come the positive value. So by this way you can change, you can control. If you vary the duty, you can control the output voltage. If you able to change the output voltage, the motor speed also will, basically it's a armature voltage control. Okay, so positive to negative you are changing that voltage value. Okay, so by this way, and your current waveform you can also see. So these four are the very basic simulations. Okay, another question I have forgotten to mention. here you can see that it's a RL load. Okay, so what will be the problem? Normally both this S1 and S4, okay, both the switch will work simultaneously, and S2 and S3 both are working complementary to S1 and S2. Means when S1 will be turned on, okay, S1 S4 is turned on, normally S3 and S2 switch will be turned on. Okay, but it's a RL load. Okay, sometimes what happen due to the current. Okay, so due to the situations of the current, sometimes current is not goes to the zero value, means there is a flowing of the current through the circuit, but unfortunately S1 S4 is turned on, as well as you have triggered S2 and S3 also, you have fired S2 and S3 also. Then what happened, S1 S2 S3 S4 all are turned on in simultaneously. Okay, in that case the short circuit condition may occur. So how do you omit that situations, means how to avoid the situation? You should design some blanking circuit. Okay, means there is some delay circuit. Okay, when that current will be zero, then only that S2 and S3 will be turned on. That conditions you have to design at the time of designing of the gate of your, or the firing pulse of your S2 and S3. Okay, similar also possible S1 and S4. Somehow S2 S3 is conducting, but suddenly turned on S1 S4. So that's why blanking circuit or dead band circuit is required for all the switches. Okay, for the turning on condition. Okay, here you are also use that RL load. So basic operation of buck converter and boost converter. So normally what happen? Normally DC-DC converter means what? It can be, you know, that buck converter. You can see the basic structure of the boost converter. Okay, it's in structure of a boost converter means step up. Okay, that voltage is stepping up from input voltage V in is stepping up to the V output. Okay, so it's a step up voltage. So how much input you have provided, that output will be more than of your input voltage, but the entire power will be same. Okay, so input power definitely equal to your output power. Okay, both the power will be same. And in case of buck converter, you can see, so input voltage, your output voltage should be less than of your input voltage. So what will be average output voltage? Similarly, you can calculate. So output voltage into turned on time T on plus output voltage into T of whole divided by T on plus T on means due T total T. Okay, by this way you can also calculate. Okay, so varying of the gate pulse, you can also check varying of the gate pulse, what happened in the output. Okay, so here we are using MOSFET IRA 450, that MOSFET is used. So MOSFET is a voltage driven voltage control device, that's why one resistance is there. So you can use your gate driver circuit also that you are preparing right now. So isolated, non-isolated, both the gate driver you can also fade here. Here directly we are taking the pulse voltage. Okay, pulse signal we have taken, but you can also use your own gate driver to drive this MOSFET. Okay, that also been possible. You can check it in your hostel if you have some spare time, and it's a current probe, so we can measure the voltage as well as current. So voltage is there in channel 2, current is in channel 1. So here you can able to see the diagram. So it's your gate pulse. Okay, and the gate pulse signal, how it will be look like, that gate pulse signal. Then here you can see the transient response of your voltage. Okay, and the current. Okay, so how much voltage you are getting? So input is how much value is there, 30.78 volt. Okay, and 25% duty you are using. Okay, and how much output voltage you can observe here, and load resistance is 28.8 ohm, and how much output voltage you are getting, more or less 7 volts. So 30 to 30, stepping down to 7 volt. Okay, so that's a step down. It's a step down MOSFET. Sorry, it's a step down DC-DC converter. So it's a buck converter. And current you can also calculate. So two configuration is there. Initially it is transient torque, then it is steady state value. Okay, initial oscillation is there, so it says transient, then steady state value. Both you can see in your diagram. Okay, so in your simulation, and put this type of diagram. So do not give the steady state one. Basically, this is your experiment number 7. So next experiment we will discuss about some control designing of your DC-DC converter. Okay, like PI control design. Okay, so basically this is uncontrolled one. So we require that transient response. So when we are using controlled one, so you can see what will be like that. How the transient response are looking like that. Okay, so it should be less. Okay, the transient will be good one, less overshoot. Okay, here you can see it's a more overshoot. So how much resistance, your steady state value is nearer to the 6.9 and your maximum value is 10. Okay, you can see 7 is your steady state voltage is more or less 7 and maximum is more nearer to the 10. Okay, so peak value is 10, then actual value is 7, so 10 minus 7 whole divided by 7. So how much percentage? 3 by 7, it is coming 42.85, 42.85 percentage. Okay, so maximum overshoot is 45%, more than 40, sorry, maximum overshoot is 43%. So if you are able to design the good control, so that value should be reduced. Okay, so this is operation of what? Buck converter operation. Then you can see for the boost converter operation. So boost
हेलो।
converter what happened? Input voltage. Hello.
मैं सर बोल रहा था बॉक का थोड़ा शो करूंगा।
Just wait for a moment. I just discuss the entire theory, then you can show it. Okay.
ओके।
Give me another 5 minutes. It will be completed. I will give the overall discussion. Then you can show your simulation, sir.
one circuit I will show them
Sure.
accordingly they
Then
have to
rest
show.
of the circuit they can complete to their hostel. Basically, it's a very simple circuits are there, and all the results and everything I have already showing here. So they can simulate it. There will be no difficulties. I think so. Basically, they have completed lot of simulations in NI Multisim, and they have lot of. I think right now they have good exposure how to work in NI Multisim, so they can also simulate. There will be no difficulties. Okay, so buck converter simulation you can show. Then rest of the simulation they can solve it in the hostel. Okay, so in case of boost converter, I think all of you have the idea. So basically that inductor here you can see for buck converter the filter inductor is nearer to your load side. Okay, that 13 millihenry and 47 microfarad. Okay, that filter inductor is nearer to the load side. Okay, so input voltage is given and input voltage, then pulses are there, so you will get that value in the buck converter. But in case of boost converter, the switch is altered. Here you can see mood diode will be goes to there, means at the place of inductor, and the control switch means MOSFET will be coming to the mood diode positions, and inductor will be shifted over here, means nearer to your input voltage in case of boost converter. Here you can see the response of boost converter. Just for a minute. Hello. Good afternoon. Actually, I am in a lab. Okay. One moment. I am in a lab. I will call you after some more time. Okay. I am taking the lab right now. Okay. Sorry for the interruption. Okay, so here you can see in case of boost converter, the switches you can see the diode and switch both are exchange. You can exchange their positions. Okay, so here mode diode is there, here MOSFET switch is there. Okay, so at the time of when that switch is on, that IR MOSFET is on, then what happened? That energy means voltage inside, sorry, voltage source directly connected to your inductor. So energy will be stored inside of the inductor, and current will be flow this path. Okay, means through the MOSFET, and the capacitor will be discharged through your load resistance. Okay, so the load resistance path. But here you can see that diode mood 160, that diode is connected such a manner, so initial conditions, so there will be no current passing from load side to the source side. Okay, and as well as when it will be shorted, so it will be less resistance path, so no current will be flow from source side to load side. So both will be isolated due to that move diode, the positioning of that move 160 diode. Okay, then initially you will get the voltage across your RL resistance. Okay, whatever voltage is stored in the MOSFET, it will be discharged through this path and will get that voltage in the oscilloscope. Okay, so so we'll get that voltage one. After that, what happened? You can see at the time of off conditions. Okay, off condition, what we can observe that voltage with your DC source plus the energy stored in your inductor, both will be connected or both will be summative each other and applied across your resistance. Okay, so directly it will coming across your resistance. So what happen, you can see the average output. Okay, average output means same formula. So v average equal to v0 into t on. Okay, durations of the on time. Okay, plus v0 into t off whole divided by t1 plus t off means total time period t. So that voltage you can observe in case of boost converter. That value should be more than of your input voltage. So it is stepping up that voltage. Okay. So from the diagram you can also see how much input voltage is there, 10 volt. Okay. So 10 volt is your input and 50% duty is there. So how much value we are getting? It is nearer to the it is nearer to the 17 mid. Okay, lot of oscillations are there. Okay, ripple is there. In case of boost converter, ripple is more compared to the buck converter. Basically, why the ripple is coming? So here you can see the filter inductor value is 10 millihenry. Okay, but in case of buck converter is 13 millihenry. Okay, but normally what happen when we are designing that boost inductor, that inductor value is comparatively less. Okay, it should be as per your switching frequency, that value will be decided. Okay, so comparatively less in case of inductor, and the inductor value is comparatively less compared to your buck converter. In case of buck converter, that value should be in the millihenry range, but in case of boost converter, that value should be in the microhenry range. If you consider a switching frequency more than 20 kilohertz. Okay, why not 20 kilowatt? In 20 kilowatt, there is a noise. Okay, some switching noise will be there, and basically it's an audible range. 20 hertz to 20 kilowatts. It's an audible range. So we have to pick. We have to select the in the switching frequency more than 20 kilowatts. That's the basic convention. Okay, and the ripple will be more in case of inductor. Okay, sorry, in case of boost converter. Okay, so here you can see the gate pulse sequence and the output voltage, output current, all you can understand, all you can also calculate it, and you can get it from your simulation also. So in case of simulation, you should show the transient response as well as the steady state response. So both are there. Okay, from the simulation you can see the current waveform, and green one is the voltage waveform. Both is possible. Okay, and so that's the basic concept. So in case of buck boost converter, so you can say like that, in buck boost converter what happened. In buck boost converter, both the operation is possible. If you changing the duty cycle range below 0.5 and above 0.5, so that boosting nature as well as bucking nature, both conditions you can observe here. Okay, so that's why it is called the buck boost converter. The simulation of buck boost converter I am not attached here, so you can simulate it to your home, or means to your home or hostel. There is not a big problem. That values are more or less same. Okay, and you can simulate it. Okay, so whatever you are thinking, if you have the interest, you can simulate it. But this 4 simulation you have to do it in your laboratory report. Okay, so I provide that material to you. Okay, so the PDF version I provide you, so you should solve it. Means you should complete it. Okay, and you have to include those value, and if I provide the soft copy, do not crop that picture and paste to your report. You have to solve it by yourself. Okay, basically at the time of exam, so we will give you the problem here. You have to solve the physically. Okay, we will allot the computer, you have to solve the problem physically at that lab. Okay, that's why you should try to submit all those simulations and complete all those simulations by the help of yourself. Okay, so that's the point. Hello, huh? Hello. अच्छा अच्छा हाँ 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 ठीक 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 ओके ठीक 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 Okay, so I think all of you are able to understand the basic idea, the basic idea of all the simulations so that I have been discussed here. So you have to solve it in your hostel and or if those are in the home. Okay, they can simulate it. So now Ramakrishna sir will share you some of the simulation. Okay, for your reference. Okay, you can follow those steps and simulate the rest of the thing. Okay, so another thing that there are two types of isolated and non-isolated DC-DC converters are available in the market. Okay, in the scenario. Okay, means in current conventions. Okay, so basically here I have discussed about only non-isolated type. Okay, sorry, non-isolated type. So isolated type I have not discussed yet. Basically that is transformerized DC-DC converter. So means you know that buck converter in non-isolated. If you go for the isolated one, it will be changed. The name is forward converter. So normally isolated converter is designed due to for what? Basically the isolation of your input side to isolation of your output side as well as the multiple output. Okay, and the mode gain. Okay, in this case the gain is not possible, but I definitely gain is possible, but in isolated the gain possible up to 10 times. Okay, so you can up to amplify up to 10 times. Okay, as well as multiple output. That's the benefit of the isolated DC-DC converter. But here we are mostly focused on non-isolated DC-DC converter. Okay, so now Ramakrishna sir will show you some simulation for your reference, and rest of the simulation you have to complete in your hostel and submit the report. Okay. And Ramakrishna sir,
Okay,
am I
okay.
audible from your side?
Sir.
Yes, yes, yes. Okay, okay. Please share. Please. Okay.
Okay. Is it students? Is it visible?
Yes, sir.
Okay. Now see the circuit. Sir has already told about this circuit. This circuit you have to do in multisim. In multisim, you will get everything except that MOSFET. Sir, here I have used IRF 1010.
Yes, yes, no problem. Okay, no problem.
And this is your battery and this MOSFET, and this is the time setting already given in manual, pulse width and time period. Okay, so starting voltage 0 to 6 volts. Then this diode is in reverse bias. This is your current probe. Ratio is same. Voltage basically it will show the signal in form of voltage, but it will measure the current. So that voltage you have to convert it to in form of current. And this is your output voltage. Output voltage across the load means R. So this net name V4 means output voltage. Net name I2. I2 means inductor current. So through analysis you can do also, or through using manually you can also plot the waveforms. So let us start the simulation. Circuits already sir already has told, and same circuit I have drawn here. Everything same. Okay. So now put grapher here. For some time you have to take this observation. Now you stop the simulation. Through analysis you can do the same. Now the voltage value is more than the current value. Now you see this. First, if you want to see the voltage value, uh, uncheck the current one, then you zoom it. Then you can take the value at any, means from starting time to at any time interval you can take the values are already given in manual. Then for current, this is your current value. Current value, as the scale ratio is very less, this waveform is not visible, we have to zoom it. This is your current value. Okay.
Sir, what is the pulse width you have given?
You have to trace. I have given in my circuit. You have to check the pulse width, whatever. Pulse width means in a square wave. Square
Yes,
wave
sir.
generator. This one.
Uh, mm, pulse width, okay.
Mm. Or you can see these waveforms are already shown one waveform of this square wave generator. Only using single channel you can do the same. This one. Scale ratio, you just less the scale ratio. Sorry. Okay, 1 minute. In graph 4 you can see the waveforms. Little bit from here you have to take from here. Okay. Yes. Now straight line will come. Just increase this time period. Then go to graph 4. This waveform is given by this generator. Okay. Square your pulse generator. Okay. Visible? All are getting or not?
Yes, sir.
So one circuit I have shown you. Accordingly, you have to do all the circuits. So circuits will be provided to you. You have to simulate the circuits accordingly and show the waveforms. Waveforms will not give you waveforms. Only this kind of circuit will give you. You have to find out the waveforms. Okay. So this is your circuit one. You take screenshot. parameter given in the above, you can see, or you can also you take the parameter here. IRFF 450 is not available in Multisim. Second circuit, this one, take the screenshot. This is for boost converter. Okay, next this one,
Hmm.
DC DC asymmetrical bridge converter. Okay, then last one, DC DC full bridge converter.
Sir, it's not showing.
Visible?
Not visible, sir. That bridge one.
अभी तक जो हुआ था वो दिखा था?
हाँ, दो दिखा था सर. उसके बाद जो दो दिखा है आप नहीं दिखा है.
अच्छा, ये वाला दिखा, अभी दिख रहा है सबको? दिख रहा है ना?
सर दैट ब्रिज वन नहीं दिख रहा है सर.
रुको
हाँ कुशल सर,
सर,
हाँ प्लीज आप एक बार स्क्रीन को ये शेयर मीन्स ये करके फिर एक बार स्क्रीन शेयर कीजिए, आई थिंक सो।
ठीक है, ठीक है, ठीक है।
नेटवर्क का प्रॉब्लम हो रहा है कुछ।